Wishes of the day. My name is Lynette Rosalind Anthony, working as Assistant Professor at the Department of Mathematics, Sacred Heart College, Calicut. Today we are going to see a small section in complex analysis, which is one among the papers for third semester MSc Mathematics under the University of Calicut. The paper name is Complex Analysis and the code is MTH3C12. We are following the textbook Functions of One Complex Variable, which is authored by J.B. Conway. So let's move on into the section, and to be very precise, we are dealing with preposition 1.5 in chapter 3, which says about elementary properties and examples of analytic functions. So let's move on to our section. To recall some among the properties we know about sequence and series, you can see as one the first recalling. A sequence in complex numbers is a set AN where n belongs to the set of natural numbers union set 0. So it is actually a function from the set of complex numbers into the set of natural numbers. Then the corresponding series of complex numbers is the infinite formal sum, summation n is equal to 0 to infinity an. So that means a0 plus a1 plus a2 plus a3 plus etc. It is going on. The third point to recall is the corresponding sequence of partial sums is defined as the sequence of complex numbers, which is the set small s naught, small s1, s2, etc., sn, where Sn in general is equal to summation k is equal to 0 to n ak, where n belongs to the set of natural numbers union set 0. So, as to illustrate, you can see S naught is equal to, here we have the n to be 0 and that will be nothing but a naught. And S1 is equal to summation k is equal to 0 to 1 ak, that is a naught plus a2. S2 becomes a naught plus a1 plus a2, etc. Sn is equal to a naught plus a1 plus a2 plus etc. plus an. So that is called the sequence of partial sums of a given series summation n is equal to 0 to infinity an. Now, the point 4 to recall is a complex series summation n is equal to 0 to infinity an is said to converge to a sum s belongs to the set of complex numbers if the sequence of partial sums set s0, s1, s2, etc., sn, etc. converges to that complex number s. So, the convergence of a series is actually here converted to the convergence of the sequence of partial sums of the series. So, that's how the convergent series is defined. So, similarly, a complex series is said to diverge if the sequence of partial sums set S0, S1, S2, etc. Sn does not converge to any S belongs to script C. Point 6 to recall is the series summation n is equal to 0 to infinity an is absolutely convergent if summation n is equal to 0 to infinity modulus of an converges. So the convergence absolutely is defined as the series of the modulus convergence. Now point number 7 to recall is the series summation n is equal to 0 to infinity a n is conditionally convergent. If summation n is equal to 0 to infinity a n converges and summation n is equal to 0 to infinity modulus of a n diverges. The eighth point to recall is an absolutely convergent series is always convergent. And we have already defined what is a power series about a fixed point A belongs to a set of complex numbers. It is denoted as summation n is equal to 0 to infinity a n into z minus a the whole raised to n. So let's move on to the next section. Product of absolutely convergent series. Suppose we are provided with two absolutely convergent series, say summation an and summation bn. We are defining a new alphabet c suffix n is equal to summation k is equal to 0 to n a k b n minus k. Here n is varying in the set of natural numbers. This is nothing but just varying k's. You can say when k is equal to 0 here it will be a0 bn. So that is the first term. When k is equal to 1 it becomes a1 bn minus 1 plus etc. plus an minus 1 b1 plus an b0. So this is what Cn is about. Now we are giving a summation to the Cn. Summation n is equal to 0 to infinity Cn. Okay? That is often defined as Cauchy product of summation an and summation bn. This is our main topic of this lecture. Okay. This summation n is equal to 0 to infinity Cn is called the Cauchy product, and how it is equal to the product of summation an into summation b. So here you can see as an illustration C naught here will be equal to A naught plus B naught. That means for C naught the n here will be 0. So we will be left with just A naught and B naught. C1 will be n is 1. That means we have A naught B1 plus A1 B naught. C2 is equal to, we have n as 2 here, and that will be A naught B2 plus A1 B1 plus A2 B0. So you can see from these instances that the sum of the indices here should be equal to the index here, and here also you can see each sum of the indices here will be 1 here, here the index is 1. Here also you can see 0, 2, 1, 1, 2, 0, everything sums up to 2 here, 2 is in here, and this goes on. You can view the following table. You are writing A0, A1, A2, A3, etc. as a row, and B0, B1, B2, B3, etc. as some column. And we are trying to multiply it. Okay? So if A0 is multiplied with B0, we write here A0, B0. A1 multiplied by B0 is A1, B0. A2 multiplied by B0 is A2, B0. And so on the rows. And here in the columns also the same way. A0 into B0 multiplied, we get A0 B0. A0 multiplied by B1 will get A0 B1, and it follows like that. And that is a table which we here talked about. So now we can see that a series summation n is equal to 0 to infinity Cn, which is called a Cauchy product. This is equal to C0 plus C1 plus C2 plus etc. So it is nothing but multiplying term-wise and summing up in this table in a particular way. See, the first C0 is here, it's A0 B0. C1 will be A0 B1 plus A1 B0. C2 will be A0 B2 plus A1 B1 plus A2 B0. C3 will be this off diagonal. See? And adding all those terms. C4 will be the next diagonal, off diagonal, like that. Okay. So each term will be the sum of the products of the nth off diagonal or anti-diagonal in the table. So now we assume that we are given two series, summation an and summation bn, which are absolutely convergent. So our aim is to prove that the Cauchy product, which we defined earlier, summation Cn, is also absolutely convergent. And to prove summation Cn is equal to the product of summation An and summation Bn. So we have two things to prove. So firstly, we will prove that the Cauchy product, summation Cn, is absolutely convergent. To prove that, it suffices to prove that summation modulus of Cn is convergent. That is a basic definition of absolute convergence of series. So we have to prove that. To prove a series is convergent, what we have to do? We have to prove that the corresponding sequence of partial sums of the series is convergent. Right? So we have to prove the sequence of partial sums. Say we are denoting here as sigma n, set sigma n, sequence sigma n of the series summation modulus of Cn is convergent. We have to prove that. So here the sigma n, we are just replacing the small n with the capital N for our easiness. Sigma capital N. So this capital N is equal to summation n is equal to 0 to n. Modulus of Cn, which is equal to modulus of C0 plus etc. plus modulus of Cn. Since it is a sum of absolute values, all the terms are positive, right? So when we are thinking about the sequence sigma n, so that means we have sigma 1. Sigma 1 will be modulus of sigma 1 will be modulus of C0 plus modulus of C1. First we have sigma 0. Yes. Sigma 0 will be modulus of C0. Sigma 1 will be modulus of C0 plus modulus of C1. Sigma 2 will be modulus of C0 plus modulus of C1 plus modulus of C2. Everything is possible. So you can see that this sequence is actually increasing monotonically. So it is a monotonically increasing sequence. And also note that it is a real sequence because we are just taking the modulus of the complex numbers. So whatever we are going to deal with now on are real. So this is a case in the real analysis scenario. Now think about sigma suffix capital N. It is nothing but summation n is equal to 0 to capital N modulus of Cn. Okay, so modulus of Cn we are replacing the series like this. Modulus of C0 is nothing but modulus of A0 into B0 plus we are replacing C1 with A0 B1 plus A1 B0. Replace Cn with the corresponding value of Cn. Okay. And we know that modulus of a product is equal to the product of the modulus. That means modulus of A0 into B0 is equal to modulus of A0 into B0. That is a property of modulus function. Similarly, another property of the modulus function is the triangle inequality. That is, if you have a modulus of A0 plus B0, suppose you have modulus of A plus B, then you can write that is less than or equal to modulus of A plus modulus of B. Okay, so both these properties of the modulus is used here. Okay, and so we can write this equality as an inequality. This is less than or equal to modulus of A0 into modulus of B0 plus we are splitting these two terms using the triangle inequality, that's why here we have less than or equal to, and then using the product of modulus property, you have this line sitting here. Okay, so you have to replace this with the mathematical series. So we are taking here, we all have the modulus of AK into modulus of BL. We are replacing it as a general term, modulus of AK into modulus of BL. Okay. And when you can see that each time what happens is, if you are taking the n as 0, we knew that adding the indices that will be 0. Here also when we are taking 1 here, the indices here will add to 1, 1. And if you are taking n here, the indices here will be taking the value n. When we add, see 1 plus n minus 1 will be n minus 1 plus b1 will, n minus 1 plus 1 will be n, and so on. So we know that the sum of the indices should be the value n. Okay, and where is this n ranging from? N is going from 0 to n. So this is mathematically written as series summation n is equal to 0 to capital N, series summation k plus 1 equal to n, modulus of AK into modulus of BN. Okay, that can be again easily written as this k plus n is actually varying, right? So from where to where it is varying? From 0 to n. Okay. So we are just making it as one series for our easiness of modulus of AK into modulus of BN. And this is nothing but summation k is equal to 0 to n modulus of AK into summation n is equal to 0 to n modulus of BN. Okay. Yeah, we are just splitting the terms and both are equal. Okay. And this is less than or equal to summation k is equal to 0 to infinity modulus of AK into summation L is equal to 0 to infinity modulus of BL. Here we have just finite values, and here we are telling that finite value will be, and that will be definitely greater than this quantity. And already we know that this series and this series sitting here are convergent because summation an and summation bn are absolutely convergent, right? So they have a definite sum. They sum up to a definite bounded value. So indeed here we have a definite bound. So that means that this sigma n is bounded by something here. Okay, that means it is a bounded sequence. Okay, so what we got here is the sequence of partial sums of summation modulus of Cn is bounded. Now we are treating a real sequence, and we have the monotone convergence theorem which says that every monotonically increasing bounded sequence will converge to the sequence. That means the sequence sigma n converges will imply summation modulus of Cn converges. Will imply summation Cn is absolutely convergent. That will end up with the absolute convergence of the Cauchy product. Now we have to prove that this Cauchy product is nothing but the product of summation an and summation bn. For this, we are defining a set of index pairs. So we can see how we define that. We are calling that set as I suffix capital N. This is equal to set of indices. Indices ordered pair k and l, such that k plus l less than or equal to 2 into capital N, and either K is strictly greater than N or N is strictly greater than N. So, if we have a confusion, you can see an illustration. Suppose if this N is equal to 3. Okay. So, for finding out what all ordered pairs are sitting inside this I3, we have to see and check for the conditions given inside the set. Okay. So when n is equal to 3, 2n is equal to 6. So k plus n is less than or equal to 6. That should happen. And either k is strictly greater than 3 or n is strictly greater than 3. Okay. So first we are taking k, the condition. Consider k is strictly greater than 3. So the first value we can take is 4. Okay. Right? The possibilities are, when k is 4, what should happen to n? We have possibilities. 4 plus 0 is less than or equal to 6. So 4, 0 is an ordered pair. 4 plus 1 is equal to 5 is less than or equal to 6. So 4 plus 1 is a choice. Similarly, 4 plus 2 is less than or equal to 6. So the ordered pair 4, 2 is a choice. Similarly, when k is equal to 5, the possibilities are 5, 0, 5, 1. When k is equal to 6, the possibility is only the ordered pair 6, 0, and we don't have any values for k which satisfies the rest. Similarly, when L is equal to 4, we have the ordered pair 0, 4, 1, 4, 2, 4. When L is equal to 5, we have the possibilities ordered pair 0, 5, 1, 5. And L is equal to 6, the possibility is the ordered pair 0, 6. And that is the end of the story. Okay, so I3 will be the set of all these values: 0, 4, 0, 5, 0, 6, 1, 4, 1, 5. I just wrote all these ordered pairs as a set. That's all. But that is I3. Now we have something to analyze. Okay, as a remark. Just we are finding what is summation KL belongs to I3, AKBL. Okay, so we have I3 here, and we are just adding the corresponding terms by selecting the indices here from these ordered pairs. So the first term will be A0, B4, see A0, B4 plus A0, B5, A0, B6, A1, B4, A1, B5, A2, B4, A4, B0, A4, B1, A4, B2, A5, B0, A5, B1, A6, B0. Okay. Now just consider summation k is equal to 0 to 3 ak into summation l is equal to 0 to 3 bm. Okay, so we are multiplying the two summations. You get in braces a0 plus a1 plus a2 plus a3 into in braces b0 plus b1 plus b2 plus b3. By using the distribution of the product and addition, you get these as the product of this. Okay. Now you just consider summation n is equal to 0 to 6 cn minus summation k is equal to 0 to 3 ak into summation n is equal to 0 to 3 bn. You can see that this difference is nothing but summation kl, order pair kl belongs to I3 akbl. Please note that this is an illustration which is used in order to generalize in the proof that what is a Cauchy product equal to. Now consider summation n is equal to 0 to 6 cn. So that is equal to C0 plus, right? C0 plus C1 plus C2 plus C3 plus etc. plus C6. So, and we had earlier said about the adding of the diagonal in the earlier table, right? So here A naught, B naught, this is C1, this is C3, this is C4, this is C5, C4, C5, and this is C6. The sixth anti-diagonal is the sum of the terms of the sixth anti-diagonal will be C6. Okay. So you have seen all the values, all the series which are used in the illustration for this equation star. This series is given with you, and we had already written what is this, and you have what is this already. And when you subtract, what happens is what that remains will be the sum of the terms in these two triangles drawn. These triangles are drawn just to make it easy for you to visualize. And when you know the terms in these triangles, you have to give a general picture or general property of these terms. So when we look at the terms, you can see that the indices of A, K, B, L, okay, K and L, here see, 0 plus 4 is equal to 4, 1 plus 4 is equal to 5, 2 plus 4 is equal to 6, here 5, when we add we have here 6, when we add here we have 6, here we have, when we add we have 4, here 5, here 6, here 5, here 6, here 6. So when we add the indices, these indices will be always less than or equal to 6, right? The remaining terms. So that is an observation. K plus L is less than or equal to 6. And also check out the indices. One among the index will be strictly greater than 3. Look, here B has an index 4, here B has an index 5, here B has an index 6. One among A, K and B L have the index to be strictly greater than 3. Here see we have 4. 4 here. For A, K we have all the K's to be strictly greater than 3. So that is another observation. So here we follow strictly the condition either K is strictly greater than 3 or L is strictly greater than 3. So from this illustration, hope you are able to follow the illustration. We are generalizing the equation star here. We have an equation star here. Okay, the star is generalized. See, when we had I3 here, this capital N here was twice that. That means here we have 2 into 3 and the rest is the same. Wherever we have 3, we generalize it to capital N, and here 6, instead of 6 we have 2 into capital N. So the star, the equation star is generalized to summation n is equal to 0 to 2n Cn minus the product of summation ak, where k is ranging from 0 to capital N, into summation bl, where l is ranging from 0 to capital N, is nothing but summation of the ordered pairs kl belongs to I suffix capital N ak bl. So we are taking the modulus of this difference. That is nothing but the modulus of this. Okay? So by using triangle inequality, again we have this term inside the modulus is less than or equal to summation, the ordered pair KL ranging in I suffix n into modulus of AKBL, and by the property of modulus function, we can write modulus of AK into BL is equal to modulus of AK into modulus of BL. And that is definitely less than or equal to summation K is equal to 0 to 2n into modulus of AK into summation L is equal to 0 to 2n modulus of BL. That is clearly seen from the table. You can analyze it from the table. minus summation k is equal to 0 to n modulus of ak into summation n is equal to 0 to n modulus of bn. And as n is tended to infinity, the term here will tend to 0. So, summation n is equal to 0 to infinity Cn is equal to limit capital N tends to infinity summation n is equal to 0 to 2 capital N Cn, which is equal to limit n tends to infinity summation k is equal to 0 to capital N ak into summation n is equal to 0 to capital N bn, which is nothing but the product of summation k is equal to 0 to infinity ak, summation n is equal to 0 to infinity bn. Just changing the letters of the indices, we have this. Thus, summation Cn is equal to summation An into summation Bn. So that is the value of Cauchy product. So that is the section for today, and hope you have understood what Cauchy product and the product and the value of a Cauchy product is. So thank you. Have a great time.